This lesson is let T be in R2, map to R2 such that T of x is equal to AX. Find a basis B for R2 with the property that T subscript B is diagonal. So here we have a matrix A, and then we're going to do A minus lambda I. Now this has already been done, so I hope that you remember how to do A minus lambda I. Okay, again, this has already been subtracted where lambda times I, so A minus lambda times I. Okay, and this has already been done just to make things go faster. Now after that, find the determinant of A minus lambda I. So A times D, which is this, minus 3 times 7. Now both of these are negative, so become plus 21, but there's a minus, so minus 21. Now subtract from, so negative and negative become plus, but there's another subtract, so that gives me minus 21. After that, multiply this out and put them in from highest order, power order, down to the smallest. So lambda lambda gives me lambda squared, minus 5 lambda, minus 1 lambda gives me negative 6 lambda. 5 times 1 is 5, but subtract 21 gives me negative 16. After that, factor it out, find the eigenvalue from the factors. So eigenvalue here is positive 8 and negative 2. Next, you will use the eigenvalue to find the basis for each of the eigenvalue. So for eigenvalue 8, make sure A minus 8I. So instead of saying lambda, we put the eigenvalue in, which is 8. Now this has already been add, subtract. So this is the result. This is the solution from A minus 8I. After that, make sure remember how to do row operation or row reducing, and that comes down to the value of x2 where I have negative 1 and 1. So now we can rewrite that as v1. So x2 negative 1 1 is v1 negative 1 1. Again, make sure remember how to times with I. After that, subtract, and this is the solution from A minus 8I. Take this matrix, do row operations, and then whatever that's left, make sure know how to write it out as a vector. So it comes out to be negative 1 1. Again, go back to the other lessons. How did we change this into this? Okay, so by row operations and write it in x2 terms, and then after that write it as a vector. Next, same thing, we have lambda, which is negative 2, so put negative 2 in, but there's another negative, so become plus 2. So it should be A plus 2I, and this is the solution after you do A plus 2I. Okay, and then do your row operations, and it came out to be this term. Now we don't want fractions, so get rid of this 7, the denominator, so multiply the 7 to it, and then I will have 3 7. So this is my v1 and this is my v2. Again, remember how to do row operation. Write out your terms in x2 or x3 or and so on. Okay, but in this situation we only have x2, so we write all the terms for x2, and then we don't want fractions, so get rid of that 7, so multiply the 7 to both, and it comes out to be 3 7. Again, this is v1 and v2. These are my basis or eigenvectors that belong to eigenvalue 8 and eigenvalue negative 2. Take these two, write it out as P. So P of V1, V2. This matrix is the basis or the eigenvectors that belong to the eigenvalue 8 and negative 2. The D matrix is just the eigenvalue only, and you put them in the diagonal and the rest just 0. So the column of P, called B1, B2, or the eigenvector of A, by diagonal matrix representation theorem, D is the B matrix for the transformation T. Okay, so the basics, the B matrix that we are looking for is the D matrix. Okay, now note this right here was written from the other lesson, and same thing with this is another lesson. So if you remember this format, they are the same thing, just written in different ways, different format. Okay, so it's the same thing, just written in a different format. Now the last one right here is pretty much the same as these right here. It's just that being rewritten again. So this last version here is another way to write this second term, this second versions, and this first version. So this version, this second, this third version, all three of these are the same thing, just written in different format. Again, first version, second version, third version is the same thing, just rewritten in different format. Okay, so this is the first version, second version, and third version. This third version is just D only. So P inverse times A times the P will gives me the diagonal. Okay, now we're going to use that to check if this was true, if this is true for the problem that we just did. So here's my D, here's my P inverse A, the original matrix, and here's the P. So for the sake of time, I already have the inverse here. So I hope you remember how to do the inverse. Okay, so the P, so this was the P right here. This is the P that we have. Do the inverse of this. Okay, this is the P that we have. Do the inverse of this. All right, so here it is again. This right here was the P, -1,137. This is the P. This is the inverse of this. One more time. This is the inverse. This inverse is this. Okay, and this is my A, the original matrix. So this is P. This is A. This is this inverse is from here. Okay, so this is P inverse A, P. So multiply this out. So just row multiply. So row times column will gives me this -6. Row times this column will gives me this 24. Row times this column will gives me -2. Row times this column gives me this -2. Bring down the P. Same process again. This row times this column will gives me this 80. This row times this column gives me the 0. This row times this column gives me this 0. This row times this column gives me -20. Now multiply the 1/10 to the whole thing, and it comes out to be 800 -2, which is our eigenvalue as we have from over here. Right here, here's my eigenvalue matrix. Okay, so again, this first version, second version, third version, they are the same thing, just rewritten in different ways. Okay, so this right here is to find A. This is to check AP equal PD. This right here is to find the diagonal. And then this part is just to show that it comes out to be the diagonal that we have. Okay, so with the eigenvalue.